great. The topic is discourse relation classification and cross-framework discourse relation classification through the lens of CCR dimensions. Okay, we'll cover the following parts. The first is we'll look at some discourse annotation frameworks that we focus on in this research, and we'll also have some look at the dimensions, and then we'll talk about the experiments. RST and PDTB are two of the most influential discourse annotation frameworks. As not everyone here works on discourse, I'll give some review of these two frameworks. The first one, RST, the phonemic rhetorical structure theory. It was developed by Mann and Thompson in 1988 and was later developed into a computational model of discourse by Markov. As you can see in this example, RST tries to model discourse as a tree, and this tree is built recursively from basic discourse units, which are called elementary discourse units, EDUs. Things like 2, 3, 4, 5 here, and they are connected with each other with a relation. Here we can see a relation named background connects EDU 2 and EDU 3. These two EDUs form a larger segment. This is called complex discourse unit, and the whole discourse is built in this way. It is believed that if a text is coherent, all the parts of a text should be connected with each other, and no parts should be left. And this is a criteria for a coherent text. And another prominent property of this theory is that it features discourse relations with different semantic salience. As you can see here, the relation that connects 2 and 3 will be represented by an arrow that points from 2 to 3. And the arrowhead points to 3. It means that this is an asymmetric discourse relation, and the meaning shown by EDU 3 is more important than 2. And if you remove segment 2, you can still get the gist of this text and without losing much information. Another because this framework has a tree constraint, you just have one relation to connect the two segments, and this is different from PDTB, as we will see later. Okay, as for PDTB, it is a shallow discourse annotation framework, which means that you can just annotate those parts where you can infer a relation. You don't have to connect every part in the text as a fully connected structure. And you don't have any constraints on what the final output would be. You just have to focus on the two segments where you can infer a discourse relation. In this example, you can see that there are two arguments. The first one is showing in italics, and the second one is showing in bold. And the implicit means that this relation is an implicit relation, and because we don't find any connectives to explicitate this relation, and this relation can just be inferred by the annotators. Except for implicit relations, PDTB also has other types of relations, such as explicit relations, and some entity-based relations. Similar to RST, the relations can be divided into subordinate relations and coordinate relations, which means some relations are symmetric and some are asymmetric. Here is an example for RST style annotation. The original text is just Treasury Secretary Nicholas Brady code. And the second, this is one elementary discourse unit, noting this single verb forms an edu here, because you can infer an attribution relation from this one and the rest of the texts. Yes, if the same text is annotated on PDTB, this is what you can get. These three relations are basically independent from each other. And the first one, the agreement, an important step forward in the strengthened debt strategy. The second argument for this would be that it will, when implemented, provide a significant reduction in the level of debt and debt service. This is still an implicit relation because there are no connectives in the original text to show this relation. But why here is a connective? Why is a connective given here? Because based on PDTB, the annotators are asked to give a connective that can explicit this implicit relation. And you can the annotators may find it possible to insert a connective given between these two arguments, and the relation for this argument pair is a contingency cause reason. Contingency is the first level sense label. The cause is the second level, and reason is the third level. We will look at this part later. There are two more explicit relations that can be inferred for this text. The first one is when. The connective is when, and this case it signals temporal relation, and because of the presence of this connective, this is an explicit relation. Another relation you can infer is still explicit, and the same arguments are connected, but this time it is a contingency relation. And even though the two texts are the same, but different relations can be inferred for them. This makes PDTB different from IST because PDTB allows multi-sense annotation, but IST only allows one relation to be annotated. In IST, we can see that there are 78 relations in total, and these 78 relations are grouped into 16 larger classes. This is just mainly for the computational use, because if there are too many labels and the data set is small, it is difficult to train computational systems. And for PDTB, we can see that a sense hierarchy is used. In level 1, there are 4 relations. These relations are general relations, for example, temporal relations or contingency relations, comparison relations, or expansion relations. Under each of those 4 levels, there are some fine-grained relations. For example, under temporal, there are synchronous relations and asynchronous relations. These level 2 labels are generally more informative and could be more useful in real applications. And level 3 mainly encodes directionality for PDTB 3. Because some of the relations are some of the relations are asymmetric and some are symmetric. For asymmetric relations, there will be a directionality. This is what level 3 does. For example, for synchronous relations, the two relations are symmetric, and there are no directionality in this relation. So level 3 leaves this part empty. And for a synchronous relation, there are two further relations, precedence and succession, to encode the directionality of this asymmetric relation. Okay, let's look at those unifying dimensions we use in the experiments. Those unifying dimensions are originally from the cognitive approach to coherence relations. But later more dimensions were added to express more relations. Those original CCR dimensions include basic operations, source of coherence, order of segments, and this is called implication order later, and polarity. We'll have a look at the meaning of these dimensions later. And the CCR dimensions are not aimed at descriptively adequate taxonomy of coherence relations, but they are aimed at deriving more psychologically plausible dimensions. And because different discourse annotation frameworks are not completely independent with each other, and people can see some correlation between those relations. And discourse annotation is generally time consuming. So there are some studies that try to integrate different discourse annotation frameworks, and the UNIDIM proposal is one of such studies. In this proposal, people try to express more relations, so they added some dimensions such as temporality and specificity, lists and alternatives for additive relations, and conditionals and goal-orientedness to causal relations. So that's the meaning of these CCR dimensions. For basic operation, we can see there are two subcategories: causal relations and additive relations. And if a relation cannot be determined on this dimension, there will be a category non-specified. This is the approach we used in our experiments. The relation of causal is, I guess, is apparent. Additive means that the two segments are put in a loose coordination relation. There are no stronger relations that can be inferred between these two segments. For source of coherence, you can see there will be the distinction between subjective and objective relations. Subjective relations means that the author's reasoning or the pragmatic effect of this relation is more important. And objective relation is just something that is the propositional contents of those two segments that make this relation possible. And the two segments form a relation, and this relation is coherent because of world knowledge. Implication order means the occurrence of events and their order in the linear text. If for this example, because he received a warning message, he didn't attend the conference. He received a warning message happens before he didn't attend the conference. So this is a basic implication order. But for non-basic implication order, it's just the opposite. For polarity, it is just a logical polarity. And if two segments support each other in terms of polarity, we call it positive polarity. And if they are it's just a position of P and not P, we'll call this negative. Some other dimensions used in unifying in the UNIDIM proposal include temporality, specificity, alternatives, lists, conditionals, and goal-orientedness. We exclude the lists in the experiments and use those temporality, specificity, these 5 to conduct experiments. These 5 dimensions are most of the time binary. these are the details for those dimensions used in the experiments. Each of the discourse relations will be encoded by those dimensions, and the specific values are shown here. So why do we use unity dimensions rather than the other proposals? Because in some studies that try to validate those proposals, they found that the results given by this unity proposal is more consistent with what they find in real data. And the second one is because unity dimensions have been shown to the possibility of automatic prediction. And the third reason is that there are some previous studies that try to incorporate those unity dimensions in discourse relation classification. In our experiments, we first tried to use those unity dimensions in discourse relation classification. The approach is very simple, but because the interests primarily on quantifying the effects of unity dimensions. The first will feed the input to an encoder. This encoder could be a language model, such as BERT or robot. Then we use the embeddings of those dimensions and concatenate the input with those dimensions, and then we feed them to feed forward feed-forward networks to get the representation, and then use we apply a classifier over the representation. The baseline is just to use the language model for classification without using those dimensions. And the second part, we use the transfer learning to show the effectiveness of those dimensions in cross-framework discourse relation classification, because PDTB corpus is generally larger than ST, so the directionality is from PDTB to ST. First, we train a model on PDTB data, and then the classifier layer of this model is freezed, and we train a new classifier layer for ST data. The number of parameters for this case would be much larger, because the parameters to be learned are just just for the last classification layer. We also did experiments on the automatic prediction of those dimensions. Because in previous works, people just tried to develop different models for each of those dimensions. Because of the relationship between those dimensions, we used one model for classifying all of those dimensions. That's the approach we take. And the results on discourse relation classification is shown here. As we can see, if we add dimensions to the input, the accuracy can be improved significantly, especially in terms of F1. We can see a big improvement. This shows the effectiveness of those unity dimensions. For PDTB implicit relation classification is a very challenging task, and we can see this very high value. But for PDTB explicit relation classification, the major improvement is on the accuracy metric. We guess the reason is that the PDTB explicit relation classification is already a simple task because of the use of connectives, and those language models are strong at capturing this the semantics of those connectives. So the performance on this task is generally generally very high. And for PDTB to RST transfer learning, we can see that there is no big performance drop, even though much smaller amount of parameters are learned for RST. But if you don't have those unit dimensions and just use transfer learning from PDTB to RST, the performance will decrease significantly. This shows a negative transfer effect. Okay, that's all for my presentation. I'm happy to answer any questions.
Thank you very much.